All right, welcome back, everybody. Today we're going to be doing section 5.4, and this section is all about the graphs of the sine and cosine functions. So I'm actually really excited to share these ones with you because I have a couple really helpful animations that I feel just make the graphs totally intuitive. These are like the standard graphs of sine and cosine that you're going to see forever and ever from here on out. We're also going to look at transformations of these graphs, but these are basically fundamental graphs. So you want to be very comfortable with them, what they look like, how to graph them, where they come from, all of that stuff. So hopefully I can share that intuition with you today. And let's go ahead and get started. All right, so, oop, there's my mouse. Okay, so this is section 5.4. We're just going to do the graphs of sine and cosine to start. We'll save the other graphs for the next couple sections. So here's the overview. We're going to look at the graph of sine, then cosine, then we're going to look at some transformations of these graphs. So we're going to look at some horizontal scalings, and then we're also going to look at some vertical shifts of those graphs. Then we'll talk about how to graph these functions by hand using key points. And that's one of the skills that you really do want to take away from this class because you're going to need it when you get to Calc 2. But I'll emphasize that again when we get there. And also, we're going to find out how to find the equation of a graph just by looking at the graph itself and being told a little bit of information. So we'll go backward. We'll start with an equation and draw the graph, and then we'll start with a graph and figure out what the equation is going to be. Okay. Yeah, so graphing in the xy plane. One thing I want to mention is that we're going to be graphing these functions in the xy plane. So x is going to be representing our input, and y will be representing the output. One second, let me do this real quick. There we go. Y will be representing the output of the function. So this is how we actually write the functions. F of x is sine of x, cosine x, tan x, cosecant x, secant x, cotangent x, and so on. So in essence, we're switching our input variable to be the letter x. Generally speaking, the symbol that we use for the input doesn't really matter, but because we want to graph it on an xy plane, where x is the input and y is the output, we're going to call theta x in this case. So if you're thinking about the unit circle, which you should be at all times, especially for today's stuff, um, just think about theta as being represented on the x-axis. Oh, sorry, x-axis. Positive theta this way, negative theta that way. But we're just going to call it x. We're just going to call it x. So how do you actually graph these things? Well, it might not be so surprising anymore, but you have to imagine the unit circle. And the unit circle is going to inform everything about what these graphs look like in a very, very deep way, as we'll see when I pull up these animations. So how do we locate the points on the graphs of these functions? We use the unit circle and the definition of sine and cosine. So just a quick reminder, sine is or here, let me do this. Sine of theta is the vertical displacement, and cosine of theta is the horizontal displacement. That's what it is. So we're going to start by graphing the sine function. So ignore cosine for a minute. And what we're going to do is we're just going to graph how this vertical displacement changes as theta changes, or as x changes in this case. The standard angles will give us our key points. So that's why you need to know those standard angles and the values of the functions at those points. The standard angles being like 0, pi over 2, pi, 3 pi over 2, and then also like pi over 6, pi over 4, pi over 3, and then multiples of things. Now the other thing is this. Sine and cosine are 2 pi periodic functions. So that means their graph repeats every 2 pi radians, every 2 pi units, right? So if you want to graph the function on the entire real line, you just need to graph one period of it on the interval 0 to 2 pi, and then graph the rest of it. You can just basically repeat the graph in both directions, and that's what it'll look like. All right, but keep the unit circle in mind, and let's take a look at the graph of the sine function. So here we go. This is what one period of the sine function looks like. How do you locate all of these points? You think about the unit circle, and you figure out what those points are going to be. So let me do this. Yeah, I'll use this. So when x is 0, or when theta is 0, the value of sine is 0. Let me use pink. There we go. Why is that? Because the vertical displacement at an angle 0 is 0. Then, as your angle increases, the vertical displacement goes up, right? So when you're at the point pi over 6, this is pi over 6, the sine has a value of 1/2. The sine function has a value of 1/2. So you get that point right there. And then as you keep increasing, when you get to pi over 2, what is sine of pi over 2? Well, I always imagine the unit circle, tip up, pi over 2, sine value is going to be 1. And so that's why we get this point here. Now, as you continue along the circle, like so, the vertical displacement starts to decrease. It starts to go down, right? So as it's going down, here's 5 pi over 6, or 5/6 pi. You're going to hit the point 1/2, and then sine of pi is 0. And then this is when you finally pass below the angle pi. So now you're in the lower quadrants for the unit circle, right? These ones down here. So the vertical displacement is now negative. It's not positive. And when we get to 7 pi over 6, we'll get negative 1/2. When you get all the way down to 3 pi over 2, so when you're like this, the vertical displacement is negative 1. And so that's why this point is right here. Right? Then, as you continue along, you're going to start to, oh wait, let me do this. As you continue along, you're going to start to tip back up. So the vertical displacement is going back to 0. And then at 2 pi, it's 0 again. And that's it. That's what one period of the sine function looks like. And then it just repeats, right? So it repeats. How do you draw the complete graph? You basically keep going this way, and just repeat that structure all along the real line. So you'll get something that looks a little bit like this. All right? So that's what the sine curves looks like. So this is actually a good time to take a minute to yourself. Let's go back to this slide. Just take a minute, and I want you to look at this graph and just think about it for a minute, all right? All right, now that you've thought about it for a minute, just say something that you notice about the graph out loud to yourself. Remember, you don't have to be talking to anybody, you're just talking to yourself. So talk to the wall, talk to your dog, whatever. Just say something out loud about this graph, something you notice about it. Okay, now let's look at the next graph. Let's look at the graph of cosine. So cosine, remember, that's the horizontal displacement. So we're going to think about how the horizontal displacement appears as we go around the unit circle to graph this one. And you might remember that when you're at angle 0, the horizontal displacement is 1 already, right? You're 1 away from the origin. So that's why cosine actually starts at the point 0, 1. So it's different than sine, right? Because sine started at 0 because vertical displacement is 0 when the angle is 0, but horizontal displacement is 1 when the angle is 0. So they look slightly different. As we'll see later on, they're actually just horizontal shifts of one another. But now let's continue along, right? So here we are on the unit circle. As the angle goes to pi over 2, the vertical displacement, I'm sorry, the horizontal displacement starts to decrease. It starts to go down. So at pi over 3, we get 1/2. And then at pi over 2, when we're pointed straight up, the horizontal displacement is 0. Now as we continue along this way, right, continue around the unit circle, the horizontal displacement is going to be negative because you're to the left origin. So that's why we get the point 2 pi over 3, negative 1/2. And then when you get all the way to pi, when you're all the way over here, now the horizontal displacement is negative 1. Then you continue around more, right? So you keep going around. Now we're pointing down 3 pi over 2. Notice the horizontal displacement starts to go back to 0. Okay, and then starting from down, we're still tipping back up this time. So we tip up this way, and the displacement goes back to 1. So when we get all the way to 2 pi, the horizontal displacement is 1 again. All right, and that's the idea. So just like before, that's one period of the cosine function. And if you want to graph the function on the entire real line, you just duplicate the graph of this period for every other period that's 2 pi in length. There we go. That's the idea. Okay, so just like before, I want you to go back to this graph. Oops, go back to this graph and just take a minute to kind of think about it. Think about what the graph looks like and try to make a bit of sense out of it. All right, now just say something out loud to yourself about this graph, something that you observe about it, something that you're thinking about it. Just say anything out loud to yourself to give your brain that feedback. All right, so this was the cosine graph. We saw the sine graph. Now, what I want to do is I want to share this animation. There's actually a lot of trigonometric GIFs and trigonometric animations online. So I encourage you to Google them if you want to know, like, you can literally just type like, sine function GIF or cosine function GIF, and there are literally tons and tons of these things that will help you make better sense of what these graphs look like and why they look like that. So here are some links on the slides that you can follow, and these will take you to the animations that I'm going to show you right now. But this first animation, I feel like, is the one that makes everything intuitive. So we're going to flip to it here. Let me pull it up real quick. There we go. And we're just going to ponder it for a minute. So let me switch to, there we go. This is what sine and cosine actually look like. So just take a minute and just stare at it and think. Stare at it and think for just a minute. All right. Okay. So let me explain what's going on here. So there's a point that's moving around and around the circle, right? It's moving around and around the circle. That's that point P that we've been looking at for the past several sections. The graph that you see, the lower graph that's being drawn out, that's the sine curve. That's the graph of the sine function because it's just literally keeping track of the vertical displacement. So as that point goes around and around the circle, that is what the vertical displacement looks like. It goes up and down and up and down and up and down and up and down. And we're just tracing out that vertical displacement as time goes on, you could say, or as theta goes on, you could say. So that lower graph, that is a sine curve, and that's how the graph is generated, which is pretty amazing. So if you can make sense of this picture, if you can make sense of the unit circle, these graphs just fall right out of it. Now, the other graph, the one that's going upward, the one that you see there, that's actually the cosine graph. It's just turned on its side, you could say. But I like this animation because it's really, really illustrating how the horizontal displacement is being tracked, right? So that graph that's going upward, that's what the cosine graph looks like because you're just keeping track of the horizontal displacement. So I encourage you to stare at this animation for a long time and just get mesmerized by it and think about what it's indicating because this is precisely how the sine and cosine graphs are generated. That's really just it. This is also why, well, this is one of the reasons I love trigonometry because this is where waveforms come from. So anything you've ever thought about that has a wave structure that you want to describe, you describe it using this. You describe it using the unit circle. So we're talking about any kind of wave, ocean waves, sound waves, radio waves, uh, any kind of waves. Even if you want to get into like quantum mechanics and string theory and things like that, this is the foundation for it. This describes any type of oscillation, any type of oscillation. So any behavior you have observed in reality that has an oscillatory nature, even like a pendulum, right? A pendulum swinging, it's really just oscillation, and it really just comes from these two graphs and this unit circle. You can stretch the graphs, you can move the graphs, compress them, you could rotate them, do all sorts of stuff, but this is how you encode oscillatory behavior with sine and cosine. All right, let's look at the other animation. That one is right here. Here we go. Let me do that a little bit. Okay, so this is basically the same picture, but what this graph, or sorry, what this animation is doing is it's showing you the cosine graph drawn horizontally, drawn horizontally. So just like the previous animation, the vertical displacement is the sine function, and here you can see they've let theta be like a yellow angle. So as theta goes from 0 all the way to 2 pi, that green point on the circle moves all the way around the circle. And then it traces out the sine function, which is vertical displacement. And then it traces out the cosine function, which is horizontal displacement. And this is what it looks like. This is what it looks like. Pretty cool, huh? I think it's pretty cool. Once again, I encourage you to stare at this picture and get mesmerized by it. Look at every little piece of it, make total sense of it, because this is basically the foundation for any of these graphs that we're going to see. So imagine the unit circle is like the, the go-to mantra for this course. Imagine the unit circle. And once you've got that down, everything kind of falls out. All right, so one thing I've mentioned, and actually I'll keep this up for a second, you might notice that the graphs of sine and cosine look very similar to each other. Very, very similar to each other. And in fact, they are the same as one another, except they're shifted. They're shifted by pi over 2 radians. So you can write sine as a shift of cosine, and you can write cosine as a shift of sine. They're just translations of one another. So that's what I've got on the next slide. So let me go back to the slides here. Let me get my mouse back. There it is. Boom. So this is it. Sine of x is just cosine of x shifted by pi over 2 radians. So this is basically the graph of it, right? So the red graph, that's the graph of cosine. Notice it starts at 1 and kind of goes like this. There's the first period. And cosine of x minus pi over 2 is this graph right here. But that's the sine curve. That's the sine curve. It looks exactly like the sine graph because it is the sine graph. So that's how they're related. That's how sine and cosine are related graphically. They're just shifts of one another. All right. That being said, let's take a look at some transformations. So what do you think these types of graphs are going to look like? We're going to look at graphs where we're going to apply this number a and this number, which actually is not a w, that's the Greek letter omega. That's the Greek letter omega. Let me write that out. Mega. Omega. Terrible handwriting. Let me try this again. A little bit better. I got to fix the tip on my Apple Pencil here. So we kind of looked at what these would do in the previous section, 1.5. If you've got this number a, that's going to give you a vertical stretching, right? And this number omega, this is where things are going to get really interesting because omega changes the period of the graph, the period of the graph. So we're going to investigate all of this now and do some examples and explore. So I said it once already, but let me highlight it here too. Oops, no, that's not what I want. That's what I want. If you change the value of a, you're going to get a vertical scaling or a reflection or both. Because if a is negative, it's going to take your graph and flip it around the x-axis. Yeah, there you go. So if a is negative, the graph is flipped about the x-axis. And just like we talked about last section, if the size of a is greater than 1, you're going to get a vertical stretch, stretching vertically. If the size of a is between 0 and 1, you're going to get a compression, a vertical compression. And the number absolute value of a, the size of that number a, that's called the amplitude of the graph. So if you've ever heard that word amplitude before, that's what that means. That's the amplitude of the graph. Basically, how far, basically it's going to give you the maximum vertical displacement. That's what it'll be, the maximum vertical displacement. Okay. Yes, okay, so that's what happens when you change A. Now, if you change omega, what that does is it results in a horizontal scaling or a horizontal reflection. So if omega is negative, it's going to flip everything around the x-axis, just like we saw in the last section. If, and this is something I mentioned, but if the size of omega is not 1, then the period of your graph is affected. It's basically going to have you go through the graph faster or slower. Same thing I talked about last time, now applied to these graphs. So if the size of omega is bigger than 1, the graph is compressed horizontally because now we're essentially what we're doing is we're going through the unit circle, this way, through the unit circle faster. If omega is bigger than 1, you're going to go through faster. round and around and around faster. But if omega is between 0 and 1, its size, you're going to get a horizontal stretch because now what you're doing is you're going around slowly. Slowly. Like if omega is 1/2 or 1/10 or 1/100th, you're going to go much more slowly around the unit circle. And so that basically stretches your graphs out like so, as we'll see. And so that's the idea. That's the basic idea with how those numbers affect the graph. Oh yeah, this is essentially what I just said out loud, but if omega is bigger than 1 in size, you're going to rotate around the circle much faster. So your graph is going to be much more rapid. But if omega is between 0 and 1 in size, then your graph's going to go like stretching out. That's the idea. So uh, let's check this out here. Oh yes, that's right, that's right. So how exactly does this affect the period and how does this affect the amplitude? This is kind of what I just said already, but the amplitude is the absolute value of this coefficient A. And the period is going to be 2 pi divided by omega. And the formula for the period makes sense, right? Because the period of sine and cosine is 2 pi. Sorry, the period of sine and cosine is 2 pi. And what we're doing is we're scaling it by a factor of 1 over w. So 2 pi over w is 2 pi times 1 over w. That's what it does. Yeah. Notice here, for example, like let's go back to the formula. If I let omega equal 1, then the period is just 2 pi, right? Which is the normal period for sine and cosine. So if this coefficient is just 1, like it doesn't appear there, then it's not going your period's not going to be affected. It's just going to be 2 pi. And the graph will complete a full cycle in 2 pi radians. Okay. All right. So let's try an example. So let's try to graph y equals 3 sine x using transformations. And for this one, I want you to try to think about it on your own for just a second here. What would it look like? What would it look like? Okay, now try to say something out loud to yourself. You've kind of thought about it. What do you think the graph would look like? Say that out loud to yourself. What do you think the graph would look like? All right, now try to draw the graph yourself, and you want to try to draw it as accurately as you can. This is one thing I'll say about just graphing in general. Your graphs are only really ever worth as much as the effort you put into them. So if you do a very hastily drawn graph, it's not going to be very helpful of a graph because we won't really know what you're trying to show or what you're trying to say. So this is an opportunity to draw a nice graph. Try to draw a very nice graph. All right, and now let's do it together. So one thing I noticed right away is that the amplitude is going to be 3, and there's no change in the period. Notice there's no value for omega, or I should say omega is equal to 1, so the period is not affected here. So what I know is this should look like the regular sine graph, but stretched vertically by a factor of 3. So let's try to draw this here. I'm going to try to draw it a little bit nicer. I'm just going to draw one period to start. Okay, here's x, here's y, and we know that normally sine would start at 0 and it would go up to 1, right? So maybe I'll say 1, 2, 3. 1, 2, 3. Right? And then here's what we're going to do. All of those standard angles, especially the quadrantal angles, those are basically going to be your guidelines. Those are going to be, they're essentially your key points, which we'll talk about in a minute. But we know that one period goes all the way to 2 pi. Pi is right in the middle. 3 pi over 2 is there. And pi over 2 is there. So we took the full period length and divided it into 4 pieces, which we're going to do again in a minute. Now, normally the sine curve would look like this. So let me start by doing this in blue. Normally sine would start here at 0, then it would go up to 1 when it reaches, when the angle is pi over 2. Then it goes back down to 0 at pi. Then it goes down here. Let me move this out of the way. Then it's going to go down here. Ah, right about, see, my graph is not totally well drawn. um, maybe I'll do this. Maybe I'll actually move my tick marks a little bit just so they're a little more accurate, a little more evenly spaced. That's a little better. Okay, so then when I get to 3 pi over 2, the vertical displacement is -1, so it's there. And then when we get to 2 pi, it's there. So these key points are what are going to help you draw the graph. So then I'm going to connect these with a continuous curve. That's pretty good. Not the best, but it's pretty good. That's the regular sine function. That's the regular sine function. But what we want to graph is we want to graph 3 times sine of x. So we're going to take what we drew and we're going to stretch it vertically by a factor of 3. So 0 times 3 is still 0. So we're going to start at 0 still. But when we get to pi over 2, the vertical displacement is going to be the highest, and so it's going to be 3. Then back down to 0. But then now at 3 pi over 2, the vertical displacement is -1 normally. But because of this 3, it's going to stretch it all the way down to -3. So we'll get this right here, and then back up to 0. So this is what our function looks like. Let's see if I can draw. Ah, that was not very good. Let me try that again. That's a little bit better. And yeah, so that's what our graph looks like, roughly, I'll say. And I do want to emphasize you should take this opportunity in this course, in these sections, in this time in your education, to try to learn how to graph these nicely. Just take the time to do it now because you don't want to draw your sine graphs like that roughly, right? Just invest the time now. Take some time to just draw them nicely, carefully, slowly, just because this is the one opportunity you'll get to do it where there's actually designated time. In the future, you'll just be required to do it. You'll just be required to do it. But that's what it looks like. Okay, now the next slide is just showing exactly what we did. Oh, wait, one thing I forgot. Now that we know what it looks like for one period, we would just extend it and keep going to get the full picture of the graph. So this would then go like this, and then like this, and so on, like that. And that's what I have here in this picture. So first there's the sine function. This is the graph of the sine function. And then over here, this is the graph of our transformation. It's basically the same graph. It's just stretched vertically. I'll point something out, and this is one of the reasons why your graphs need to have labels. They need to be labeled well. If you just look at these two pictures side by side, it looks like the picture on the right has been squished horizontally, right? Like horizontally compressed. But that's not at all what has happened here. And you can tell because if you look at the actual labels, if you look at the tick marks and the labels on the tick marks, they tell you where the points lie. So over here, this is the point 2 pi on this graph, but over here, this is the point 2 pi on this graph. So even though visually it looks like there's a horizontal compression, there isn't. And how do we know that? Because we're literally looking at the labels on the graph. So when you draw your graphs, you must include labels. You must include labels. Label the tick marks. Draw the axes straight. Plot points and label points. Give as much detail as you can to your graph. So that way when somebody looks at it, there's no ambiguity whatsoever. That's what you're going for. No ambiguity. We shouldn't have to wonder if that's the point 2 pi or if that's like, is this getting squished or is it stretched? Where do these points, we shouldn't have any of those, or I should say, we should have answers to all of those questions when we look at the picture you drew. That's what you're going for. All right, let's try another example. So let's try to graph 2 times cosine 3x using transformations. So think about this one on your own for just a minute. Think about what it would look like. All right, and now just say something out loud to yourself. Describe how you think it would look like using transformations. All right, now you try to graph it on your own. Try to draw a nice graph with straight axes and labels and all of that stuff, and then we'll do it together in just a moment. All right, so let's try to work on this one together. And I think what I'm going to do for the sake of time, because I do want to get to the thing about key points. Yes. Yes. Okay. So for the sake of time, rather than draw the whole thing out myself, I'm going to go to the next slide, which has the different transformations on there. So we're starting with this graph. This is the cosine graph, right? Just the standard cosine graph with no transformations. Then the first thing that they did was scaled it vertically. Scaled it vertically. Yeah, that's it. So scale the whole thing vertically. And now the maximum displacement is going to be 2. The minimum is going to be -2. But that's all they've done for this step. This is just the first step. So notice here we started with cosine. This is the graph of 2 times cosine. Now they're going to change the period. So remember this number 3 here, this number omega, that's going to affect the period. And I encourage you to think about it in terms of speed. Because that number is 3, that means that we're going to get a horizontal compression because we're going through the inputs 3 times faster than normal. So our graph should be compressed. There we go. So here's the graph of 2 cosine x, like we saw on the last page. And then this is the graph of 2 cosine 3x. So again, notice that the graphs actually don't look different in shape, but they are different. And the labels on the graph are what verify that. The labels are what give us all the information. So you must include these types of labels. Notice over here, this point is now the point pi over 3, whereas before it was just pi. Which makes sense because our period is changing by a factor of 3, right? So it's going to squish everything. It's going to squish everything. So normally where we would land at the angle pi, we're going to land there at the angle pi over 3 because we just went through 3 times faster. So a shorter distance, right? A shorter amount of time to get to that same point. And that's what it looks like. We're going to do some other examples like this in the next few slides. So if this doesn't make sense yet, that's okay. We'll do some more examples and you'll practice on the homework as well. All right, but now let's add in some vertical translations. We already saw that A affects the amplitude, and we saw that omega affects the period. The constant term that you see in these formulas up here, this B, what that does is it gives you a vertical shift, just like we saw in section 1.5. So that's the only thing that changes. Everything else is the same, except now you get a vertical shift. So here's another one. Try to graph this function using transformations. So just like before, think about it for a minute. Right? And now say something out loud about the graph, just what you can tell by looking at the equation. What do you think the graph is going to look like? All right, now you try to work on it yourself. Try to draw the graph out, a nice graph with straight axes and a pretty decently drawn curve, and then we'll take a look at it together in a moment. Okay, so uh, for the sake of time, I'm gonna go to the next few slides to see how the transformations look, and then we'll see how to graph this by hand when we go to how to plot with key points, which is later on here. So if you're just using transformations, this is how you would get it to come out. So over here, this right here Actually, they have both here. My apologies. This is the graph. Hold on. What is pi? Yeah, there we go. So this is the graph of -4 cosine pi x. Then you apply the shift of -2 units to get this graph, just like just like so. All right. How to find those points and how to get those graphs by hand, like this one, we're going to do in just a minute. But what I want to do now is go to this Desmos example. You can click on this link yourself, and it'll lead you to this Desmos example that I'm about to pull up here. And you can mess around with all these numbers and change these graphs. So let me share it here. Here we go. And the letters are a little bit different. So for example, A is the same, but D is B on the in the formulas on the previous slides. But just remember that when you're adding something after the function is applied, you're getting a vertical shift. So what I'm going to do now is vary some things. The red graph that you see here is the graph of the sine function. There we go. I'm not going to change C yet. This number C actually affects the phase. That gives you a phase shift, which we'll talk about in point 6, I believe, is where we talk about it. But look what happens when I change A. There's my sine function. If I increase A, it gives you a vertical stretch, exactly like we would expect, right? So when A is 6, the vertical displacement maximum is 6. Now, if I make A to be smaller than 1, right? Here's the regular sine graph. If I go less than 1, if it's like 0.7, 0.6, 0.5, it's compressing the graph vertically because we're taking the output of the sine function, the outputs are the y values, and we're cutting them down by half. We're literally multiplying them by a half, so they get shrunk and they squeeze down. And the smaller A is, the more compression you've got. See, and then it goes to 0 even. So if A is 0, you don't really have a sine graph anymore. You just have 0. You have the line y equals 0. Now watch this. So if I go negative, everything flips upside down, but then the size of A still affects the amplitude. So now if the size of A is still between 0 and 1, I get a compression, vertical compression. If the size of A is bigger than 1, I get a vertical stretch, just like that. But now, because A is a negative number, here it's -4.5, the entire graph has been flipped vertically around the x-axis. So check this out. Let me go back and forth between negative and positive values. Check this out. There it goes. See, there's the flip. Flip, 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 flip. And that's what it looks like. All right. So now let me go back to amplitude 1, just a standard sine curve. And now let's mess around with the number b. So we were calling b omega. We were calling the b omega. So remember, that will change the period of the curve. So check this out. When I increase b to be something that's bigger than 1, watch what happens to the graph. It gets compressed, right? It's basically taking the graph as it was and squishing it down. Because remember, if b is a number that's bigger than 1, you're going around and around the unit circle faster than before. So what that corresponds to is going up and down a lot faster. So if the size of b is bigger than 1, you get horizontal compression. Now, if b is between 0 and 1, look what happens. Let's go down to 1. Okay, down to 1, but now if I go below 1, it's stretching it out, stretches it out quite a bit. Whoa, look at that. So when b is 0.1, when b is 1/10, that means you're going around the circle 10 times slower than normal. So that really, really affects the period. Really, really affects the period. So now the period is like way long. There we go. Way longer. It's hard to see on this particular zoom out, but the height has not changed. The height is still 1. So if I zoom in a bit, where is it? Where is it? Right there, right? So the height is still 1. Nope, right there. But now it's reaching that peak at 5 pi, at 5 pi instead of pi over 2, right? Because we scaled everything. So there you go. Let me go back to the standard view. So that's what that number b does. Changes the period of the function. Now, if b is negative, you get horizontal reflection. Just like that. You, 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 you. Maybe even as I move these things, maybe you can almost see like sound waves, right? Maybe you all have seen animations like this before in movies or shows or something like that, right? Well, if you're interested in anything like electronic music or music creation, this is how you do it, quite literally. You basically tweak sine curves and cosine curves, and when you change the frequency of the curve, it changes the way it sounds. When you change the amplitude of the curve, it changes the way it sounds. All of that stuff affects how it sounds. How do you go through those things? They're just transformations of sine curves. That's really all it is. That's really all it is. So stuff to ponder, right? You always want to ask, when am I going to use this in life? Why should I care about this? Why is this important? Why am I learning all of this stuff, right? Well, you're learning it because it's going to give you an incredible ability to describe things that are oscillating, even if it's like sounds or anything like that. It's highly applicable. It's actually it's insane how applicable trigonometry is. I hope some of you get to take a class on Fourier analysis later on, but Fourier analysis essentially lets you take a signal, a radio signal or a sound signal that's got a whole bunch of these different tones overlapping each other, and it lets you pull them apart into the individual fundamental frequencies. It's really, really fascinating. It's actually like how you decode transmissions that you intercept, that kind of thing. Okay, so let me put B back to 1. There we go. So no change in period, no change in the amplitude. We're going to skip C for now, but let's look at D. So let's look at D. D is this number right up here. And as we had seen before, that's going to give you a vertical translation, right? A vertical translation. So if D is positive, it shifts the whole graph up. If D is negative, it shifts the whole graph down, and that's it. And then you can mess with all of these numbers, all these values to get different types of sine curves. There you go. Pretty cool, huh? All right, so you have access to this Desmos example. You can play around with it some more if you would like. Let's get back to the slides and talk about how to graph these things by hand. So generally you want to ask yourself, okay, great. So if I had a graph, I could see what it looks like, but what if I don't have the graph? Well, you've got to be able to make it yourself. That's what you got to do. And we're going to do that right now. So generally speaking, functions that are transformations of the sine and cosine functions are called sinusoidal functions. So if somebody uses that word and they say, oh, it's a sinusoidal curve, what they mean is it looks like the sine function, but transformed in some way. We're going to explore horizontal translations in 5.6 because those can get a little bit tricky in terms of what they are, particularly because omega affects that. So we'll talk about that one later. For now, we're just going to do period changes, changing the amplitude, and vertical shifts. That's what we're going to focus on for now. Yeah, so horizontal translations are actually called phase shifts, but we'll talk about that later. So how do we graph these things? We're going to graph them by using key points. And what are the key points? The key points are basically the points that occur at the transformations of the standard angles. So if you know those standard angles, that's going to help everything out. That's all you really need to know. And we're going to tweak those. All right, so here is the checklist for how to graph these things using key points. And we're going to start with, let's see, did I do that one? I think I saved the, do I save the, I guess I saved the vertical translations for, oh, no, it's basically the same. So, yeah, it's basically the same. So how do you graph these things? Well, the first thing is you need to find the amplitude and the period. So number one thing you do is you say, what's the amplitude? What's the period P? Then you're going to take the interval from 0 to P, whatever that period is, and you're going to divide it into 4 equal length subintervals. That's step 2. So find the period, take that number, divide it by 4, and that's actually going to give you your key points. So use the endpoints of those subintervals to find and plot 5 key points on the graph. Then you connect the points with a sinusoidal curve. So once you have those key points, you connect them with a nice smooth curve. Then, last but not least, extend the graph in each direction to complete it. So that's how you got to do. Quick run through again, find the amplitude, find the period, divide the period by 4 to get 5 key points, plot those key points, and then connect the points with a curve. That's the idea. All right, so let's try this one. Try to think about this one on your own. So first, think about how you would approach it. All right, now try to say something out loud to yourself about how you would approach it. Okay, now see if you can figure it out yourself. Remember, you're going to graph it, so try to draw a nice graph, a graph that's well drawn with axes and labels and points and a nice curve that connects the points, a nice curve. Okay, now let's do it together. The first thing we need to do is find the amplitude and the period. So I can see right away that the amplitude, let me use this. The amplitude is going to be absolute value of 3, which is 3. And the period here, remember, what's the period? What's the formula for the period? Well, sine normally has a period of 2 pi, but we're dividing it by 4. So it's going to be 2 pi over 4, because our number omega is that number 4. But 2 pi over 4 is just pi over 2, so that's our new period. That tells us that the entire graph, I'm sorry, the one whole cycle is going to occur in pi over 2 radians instead. So whatever the sine graph looks like, right? This is going to occur in pi over 2 radians instead, roughly speaking. Okay. All right. Now, remember that the third step says once you have that number p, divide it by 4 to figure out where your key points are. So that's what I'm going to do now. P divided by 4 is going to be pi over 2 divided by 4, which is pi over 8. So at basically increments of pi over 8, we're going to have a key point. So as in like 0 pi over 8, 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. Wait, how many is that? 0, 1, 2, 3, 4. There we go. And then those are where you're going to draw your key points. So let me draw my graph here. Okay, I'll start with this. Okay, this is x, this is y. The amplitude is 3, so the height is going to be 3 and negative 3. The period is pi over 2, so this is actually going to be pi over 2. And now this number, pi over 8, that's going to be what we count by. So we're going to start at 0, that's 0 pi over 8, then we're going to do 1 pi over 8, 2 pi over 8, 3 pi over 8, but then 4 pi over 8 is just pi over 2. So we'll have made it. All right, let me graph this. So this will be like this. There's our little points. So 0 pi over 8 is at the origin. This is going to be 1 pi over 8, 2 pi over 8, 3 pi over 8, and then 4 pi over 8. And there's no reason for you to simplify those fractions if you don't want to. I actually find that it's more convenient to not simplify them, to just leave them as multiples of pi over 8, because then you can quite literally just count, right? Remember I was saying earlier, just appealing to counting over and over and over in this course. Okay, so now what does the sine curve normally look like? It normally looks roughly like something like this, right? Except now all of those peaks and troughs, those peaks and valleys are going to occur at these points. So let's try to graph it like so. All right, sine starts at 0, then it goes up at pi over 8, then it's going to come back down to 0, then it's going to go down here, and then it's going to go up here. So our graph should look something like this. It's not too bad. Not too bad. There we go. And that's what the graph looks like. And we're done. That's pretty much it. So, then we have to extend it, right? So then once you have this, you can extend it either direction and have it go on more. So let's look through the slides now. This just kind of walks through the work that we did. P over 4 is pi over 8. Here are our key points. And then this is what the graph looks like. So this is what we just graphed, right? Not too bad, right? Not too bad. Okay, let's do another example. So let me throw this one on here. And just like before, I want you to think about it for just a minute. Look at it, think about it. Okay, now I want you to just say something out loud to yourself that you observe about the graph, anything at all. All right, now you try to work on it on your own. Remember how to do it, find the amplitude, find the period by 4, plot those key points, and then connect the dots. So you try it on your own, and then we'll do it together. All right, here we go. Just for the sake of time, since I know this is getting to be a bit of a long lecture, I'm just going to use the slides rather than draw it all out by hand again, but the process is the same. So you can always go back to that previous example. First thing you do, find the amplitude, find the period. One thing I'll point out is this. Notice that the period is normally 2 pi, but that number omega is 1/3. Omega is 1/3. So we're going to take our period and divide it by 1/3, and that's what's going to give us 6 pi. And again, you should always go and check the intuition, right? Omega is less than 1 in size, so our period should be longer than normal. We're going through at 1/3 the speed we normally would. And this agrees with the number that we got, right? Because 2 pi divided by 1/3 is going to be 6 pi, so our period is now, it's not 2 pi anymore, it's 6 pi. Divide 6 pi by 4, and you're going to get 3 pi over 2. So that's where all of your key points are going to be. 0, 3 pi over 2, 1, 3 pi over 2, 2, 3 pi over 2, 3, 3 pi over 2, and 4 times 3 pi over 2, which is 6 pi. There you go. 1, 2, 3, 4, 5. All right. Another thing I'll point out before we look at the graph, notice that the number a here is negative. So because a is negative, it's going to take the whole cosine graph and flip it vertically about the x-axis. So keep that in mind. It's going to look like cosine, but it's going to be vertically stretched. It's going to be flipped, and then we're going to stretch it out horizontally too. So once you take all that into account, plot your key points, connect them with a line, and you should get something that looks about like this. Yeah. So it's flipped upside down. It's going from -2 to 2. Our period is right there. 0, 1, 2, 3, 4. Hold on a second. I think I have a typo there. 3 pi over 2. I do have a typo. I apologize. This should be a 3. That should be a 3, not a 4. My apologies there. But that's what the graph looks like. Okay. All right, moving along here. Let's try this one. So this one is similar, except now we also have a vertical shift. So just like before, take a moment and I want you to just think about what this graph could look like. All right, now I want you to just say something out loud to yourself about what you think the graph would look like. Okay, now try to graph it on your own. Usual guidelines. It should be a nice looking graph. Remember to find the amplitude, find the period, divide the period by 4 to get all those key points. And then this one, you're going to have a vertical shift as well. So you can apply that after you've found all the key points. Or I should say the values of P over 4. Okay, now let's take a look at it together. So once again, just for the sake of time, I'm going to use the slides to my advantage here. We find the amplitude and period. The amplitude in this case is 4. The period is 2 pi over pi, which is 2. So again, normally the period for cosine is 2 pi. Omega in this case is the number pi. So we do 2 pi divided by pi, and we get that our period is 2. One thing I'll mention here, because sometimes this throws students off a bit, there's no rule that says your period has to have a factor of pi in it. So just notice here we just get the number 2. That's totally reasonable, totally allowed, and very, very common. Uh, because omega is already at pi, it kind of gives us a nice scaling. I'm sorry, because omega is equal to pi, it gives us a nice scaling. So now we can make the period 2 instead of like 2 pi, for example. Okay, now that we know the period is 2, divide the period by 4 to get the locations of your key points. So 2 over 4 is 1/2, and then you just count them off. Oh, there's another typo. I apologize. So 0, 1/2, 1, 1/2, 2, 1/2, 3, 1/2, 4, 1/2, and this should not say 6 pi. That should say 2. So I'll fix those as soon as I finish the recording here. All right. Now, the only other thing that's left is this shift of -2. Well, actually, there's a couple of things. One, we're going to take that graph and we're going to shift it down by 2, but also A is a negative number here. So that means that it's going to be the graph of cosine, but flipped vertically again. And then because the amplitude is 4, it's going to be a vertical stretch. Right, putting it all together, we have something that looks like this. There we go. That's right, that's right. This is the one we saw earlier. That's right, that's right. That's why I put this here. So there we go. So earlier where it was like, how do we find these key points? This is how we find these key points. Find your period, divide it by 4, and then you can plot everything. Okay. All right. So now, last couple examples here. I think I only have one. Yeah, last example here. What if you had to go in reverse? So what if instead you were given a graph of a sinusoidal curve and asked to find the function itself? How would you do it? So pause and think about that for a minute. Let me throw up the thinker. Think about what I just said. If you were given the graph of a sinusoidal curve, how would you find the equation or the function for that curve? Okay, now let's try to work it out on our own. We know that the key points come into play. We know that omega is going to change the period and A is going to change the amplitude. So just looking at the graph, one thing I noticed right away is that that peak has a height of 3. So that tells me that A has got to be 3 or -3. That's the question. Let's see. It looks like it's going to be +3 because roughly speaking, this looks like a cosine curve. Looks like a cosine curve because it's like starting at the max, then going down to the, sorry, starting at the max, going down to the min, and then back up to the max. So it's probably going to be cosine. Oops. It's going to be 3 cosine something. Now, is there any kind of vertical shifting? No, there's no vertical shifting here. There's no like the center line, you could say. The center line is still on the axis. So there's no vertical shifting. But the period is not going to be 2 pi. This one actually tells us the period is this length. So here they're saying the period is equal to 1. Okay, well, if the period is equal to 1, and we know that the period is 2 pi over omega, we can solve that for omega. That's what's going on right here. So the period is 1. So that means 1 is 2 pi over omega, which means omega is 2 pi. So last but not least, we can put this together, and this is what our function is going to look like. 3 cosine 2 pi x. All right, let's see. Is that right? Yes, that's it. And so that's what our function looks like, 3 times cosine 2 pi x. Since I had mentioned it in a previous slide, one thing I'll point out again here is that it's actually very common for the period to be shrunk to 1, because then you basically have an entire cycle occurring in a length 1. So that can be really helpful later on. All right, but I think that's about it. Let's see. Yep, that's it. So let's play. Now you should try to do the homework. If you've got questions, you can post them on the weekly discussion. But that's about it for this lesson. The next section, we're going to talk about the other graphs. So we'll do tangent and cotangent and cosecant and secant in the next section. That's what we'll do. But if you want to know roughly what to expect, it's going to depend on sine and cosine a lot. So, just like before, what do you really need to take away from the last couple lessons? The unit circle, making good sense of the unit circle, understanding what the graphs of sine and cosine look like, and then that's going to help you do all of the other graphs. And actually, it's pretty amazing how, frankly, how simple it is to graph something like cosecant or secant if you know how to graph cosine and sine, or I should say sine and cosine. But we'll see that in the next section. So until then, happy studying, and I will see you next time.